answering the questions right away, or to keep them until the end, or yeah, maybe for having some interaction, we can do it right away after the audience, somebody raises hand.
It's up to you. Like, I'm
Yeah,
ready
okay,
for
sure.
interaction.
Yeah, I'm going to looking through the chat, through the live chat, and I'm going to be looking on the raised hands and let you know if there will be some questions. I think we are good to start right now. And if you have something to share, I mean, your presentation or desk or anything else, just you can start doing this. And without further ado, I would like to pass the mic to you, and the floor is yours. Good luck.
Yeah, hi guys. Can you hear me? Can you see the screen?
Yes, yeah, it works.
So you can see the screen and also like arrow, yeah, like I mean mouse here. Great.
Yeah.
So yeah, as Alejandro said, so my name is Mike. I'm working at Fluence Labs. So we're actually doing decentralized serverless computing platform. And today, like, I'm going to split our session. So we have like 1 hour session. I'm going to split it into 2 parts. The first one will devote it to some, let's say, theory regarding what we are doing, what are our main components, how they're connected, and what actually is decentralized computing platform. Because actually there was not so much examples of such platforms, and I will show you some basics and some like some main component that we have, and we'll highlight like our main like differentiation points from AWS Lambda. And then on the second part, we will go through our execution engine called Marine, and we'll try to build simple services that intended to run on Fluence network on decentralized fashion. I will show you that it's not it's really similar to experience that you have in Rust. Okay, let's start with the first part with like Fluence. So actually, if we're talking about like Fluence, where it consists of several parts. The first one is what we call cloudless stack. But this stack, we mean that's actually it's a part of it's like our main components. It's tooling, it's execution engine intended to run functions. Also, there is compute marketplace that intended to incentivize all of that, and also DAO to control like marketplace and to control like ecosystem. One of the main, let's say, analogy for see what we're actually doing is Amazon Lambda. We can say, by the way, guys, let me clarify. You see my slides, yeah? Because I don't see them on the screen. I see only like
yeah, that works. We see your slides.
Great. Thank you. So if we compare what we are doing compared to AWS Lambda, so then there is a like on the left side, you see here that, for example, in Amazon Lambda, there is an engine that's intended to execute functions. And in our case, in case of Fluence, we are using WebAssembly. We have our own engine called Marine. It's intended to run WebAssembly modules. In the future, we're actually working on containers. And in the future, we will like allow more or less arbitrary Docker images to run in our cloud. The second key features of Amazon is AWS step functions. Actually, it's a workflow engine. It's like functions intended to run different Lambda functions. Yeah, it's actually like second level of functions. And in case of Fluence, we have a so-called cloudless functions. We have our workflow engine called Aqua VM. This engine intended to, like, it's actually based on PyCalculus. I will show you on the second part of the slides what are the main benefits of having such a new workflow engine. But in short, it's intended to run functions in decentralized networks without like knowledge and without complexity of these decentralized networks. And also, like on Amazon, there are a lot of amenities. Yes, that allows you to load balancing, to routing, to scaling, to orchestrate something, deploy, and whatever. And one of the main benefits of like Fluence is our language called Aqua. And this language actually could be considered as a language where you can specify your protocols. So you can describe protocols in language, and with different Aqua libs, so you can import libs as in like usual language, and this libs provides you different functionality. And for example, they can provide you different protocols for load balancing, for consensus, for whatever. So actually, it's written as a libraries in our language. Okay, what's the main? Let me probably second. I will play it in a window. Yeah, can I do it? Oh, yeah. So you see it as well, yeah. Okay, what's the main complexity of doing decentralized compute? I think all of you know that just compute like is difficult. Yeah, that's Amazon was working on their like engines for a long time. There are like other clouds like Google clouds, like Yandex clouds. There are a lot of them. So just compute is difficult. But in decentralized compute, we have another like dimension of difficulty, and this dimension actually is that we should care about that every participant in a network could be malicious. By that I mean that they could like tamper like network packets that came along this peer. They could provide like incorrect results. They could be incorrect. They could be malicious, or they could be incorrect, as well as like in different things. And in Fluence, we're trying to deal with such a complexity and trying to like provide a way to write functions as usual, but this function could overcome such a complexity of decentralized networks, where some parties could be malicious. Okay, and how we actually achieve that? Let me share you like some basics about our protocols. But first of all, we need to consider how it works generally and which user types do we have. So actually, we have several user types. For this talk, it's important to note 4 of them. They could be considered like 5 to 6. But for us, it's important that we have developers. There are like people who can run their application on some compute, and we have capacity providers. Capacity providers, they are mostly data centers that have like hardware that they wanna like utilize, and they can and they can participate in Fluence and provide their hardware in decentralized fashion. And developers, they will like eventually deploy applications on some capacity providers. But also there is another type of user, we call them just users. These user types, they are using application. Yep. And developers provide access to application by some tokens to this user. And user actually goes to hardware provided by capacity providers and use this application. And the last part here is the blockchain. So by blockchain, I mean that there is an on-chain layer intended to incentivize all of this like scheme with several developers, and developers pay for, they don't pay like directly to capacity providers for the service. they pay through blockchain, and then this blockchain eventually distribute rewards to capacity providers. And also remember that every part here could be malicious. For example, there could be malicious capacity providers. What does that mean? It means that, for example, that those guys, they can say that, oh, I have hardware, but actually I don't have hardware. Yeah, and to overcome such a problem, we have a protocol called capacity commitments. It's intended to prove that capacity providers actually allocate hardware for Fluence network. So like all providers, like from all peers, they should submit capacity proofs that this hardware, to show that this hardware allocated for the network. And this is for like capacity proofs. So as I said, we have two main protocols. The first one is the cloudless functions. I will refer to it as a useful work protocol. It consists of several parts. The first part is the execution engine that we'll like talk in the second part. It's our marine. I will show you some examples how to run functions. Second is a workflow engine, it's called VM, and also SDK tooling. And the second protocol is a compute capacity commitments. This one is intended to prove that hardware belongs to the network, and it can consist of several components. The first one is a daemon that actually creates proof, and it's run internally on the hardware of capacity providers. And IPC, by IPC here I mean our blockchain. We are using interplanetary consensus blockchain by Protocol Labs. And this layer validate proofs and also like coordinates all the work in the network. So the capacity commitment protocol constitutes mainly like blockchain and capacity providers. So both developers and users, they don't know anything about that. They shouldn't consider this additional level of complexity. It's kind of solved between blockchain and capacity providers, and developers just need to write like functions. And regarding useful work, regarding cloudless protocol, it's like includes all roles, all user types, and all of them should be aware of such a protocol. Okay, let me briefly describe capacity commitments, like in several slides, and I will describe in more details our workflow engine because it's one of the probably most innovative part in Fluence. So in capacity commitment protocol, we divide every hardware to compute units. Compute unit is basically one physical core with 4 GB of RAM and also like 10 GB of virtual disk. And for each compute unit, so like every physical service is divided into such compute units, and for every compute unit, there is a like proof that it was belonging to like to Fluence network for some epochs. Yeah, for example, for epoch and Fluence is 1 day. And compute provider usually has several peers. All of them, they are divided into compute units, and compute providers can like sell these compute units to Fluence, and they will be like compute providers, they will be incentivized by the fact that they're like allocated compute units for Fluence. And also, as already said, that's like compute units, they should provide proof of capacity. And actually, each compute unit could participate either if in like proof of like capacity commitment protocol or in cloudless function. So it's needed because sometimes there is not enough load, not enough like usage of such compute units by useful applications, by applications that's paid by developer. And in this case, they could switch to capacity commitments and provide proof of capacity. If not, they will provide a proof of usage in this second protocol, cloudless functions and useful work. And this is also like developer and user, they both don't know anything about like these proofs. They are built into protocol, and they are like kind of free from terms of developer experience and user experience for both user and developer. Okay, so usually in compute providers there are several peers. Some compute units, they are devoted to like network and they participate in proof of capacity, and some they are doing like useful work. And also the last slide in this section is about compute marketplace. So in compute marketplace, we have like actually in Fluence, we have on-chain and off-chain part. On-chain, we have it's run on IPC, as already said, and there is a bunch of contracts And on this contract, there is offers and all information about providers, all information about deals, whatever. And off-chain part that consists of compute providers that's allocate their hardware for Fluence, and they have like corresponding information on the on-chain part. And it's called marketplace because compute providers they like sell, let's say, their hardware for some time to Fluence, and the developers can come and say, oh, I want like, let's say, hardware for such a period of time with such like settings. I will describe settings a bit later. With such settings, and then like market making is done, and some offers are produced that developers will use such compute units from one or more providers as a part of some particular deal, of the on-chain deal. Okay, it was about like Fluence in general, and let me show you briefly one of the most interesting part about a workflow engine. And let me start here with a like, let's say, a bit theoretical model. So imagine that we have peers. On peers, we have something that we can call local compute. It's actually a function. Yep, it could be stateful or stateless, factful, whatever. This function has some inputs and some outputs, so we can represent it by this, like this string. CID here is a content identifier. It's actually a hash of some fancy hash of arguments and values. Yes, that could be used as arguments or outputs of this function. And on the like second part, I will show you how to write this fpeer as this local compute, because for like global compute, so if you need a bit more time, I will show you some like links when you can, our quick starts when you can do it, but we will need like more time. And the purpose of workflow engine is to try to build a composition of such functions. Imagine that we have different peers, they have different local compute, and we need to compose them somehow. And also remember that we are working on decentralized world when every part could be malicious, and we need to be aware of that. And also it's need to be hide inside protocol to make UX and DX like fancy for user. And there are also much more questions to answer, yeah. And we did some research before starting this workflow engine. We did it like 3 years ago. So we are actually working on such protocol more than 4 years. And 3 years ago, we researched what's actually our like current solution for a problem of workflow engine and decentralized networks. And it turned out that there wasn't like any solution. There wasn't any like a, let's say, framework, whatever, to orchestrate decentralized compute or actually to express them. But actually, there is like a lot of theory behind. And actually,
Sorry, Mike, could you please let me know if you are still on the fourth slide?
No.
Because people are asking in the live chat. I think your screen is frozen and the pages are not advancing.
I'm sorry. Let me try to reshare.
Okay.
Can you see it? They should
Oh, yeah,
be changing.
yeah. Now the pages advance. Okay, yeah, perfect.
Yeah, there were some slides for protocols. Yep. So let me just briefly describe. So there are 4 types of users, 2 protocols. The first protocol is for proofs of like capacity commitments that some hardware belong to like Fluence. Second protocol is call those functions. That's for useful work, to express useful work. And now I was talking about workflow engine, and here it's a bit theoretical problem statement that we have a local function and we have several local functions that's located on a peer, and we want to compose them. Yep, and there are a lot of questions, and I stopped here. That's actually the main observation that's lying on the foundation of our workflow engine. That's if we are able to express fork join pattern, then we actually are able to express any compute. Yep, it's it's correct also not only for decentralized but for just Web 2 world. Yep, because workflow pattern is actually lies behind the OpenMP, MapReduce, and many other framework and platforms. And we tried to find a theory for this fork join pattern. And actually, one of the most suitable theory was PyCalculus. PyCalculus is a fancy, well-known theory that describes communication channels or communication parties. And one of the most important here is the combinators. Combinators is a way how you can join different computations together. And there are a lot of versions of PyCalculus, but in the most basic one, there are three combinators. First one is sequential compute, when you first execute one function and then another. This one is a parallel, when you can run them in parallel. And this one in the middle that's represented by plus is actually a sign for executing with error handling. I mean, imagine that if P for some reason not executed, then we try to execute Q. In theory, it's a bit more fancy, but I'm talking mostly how it works in real case, in our case. Also, there are some more aberrators here. For example, for representing cycles, we're using replication. Also, there is a match mismatch, so it's for if and else. Yep, and the main part is channels or names that can communicate to each other through these channels. I mean, process could communicate through these channels with other processes. Okay, let me show you an example why all of this needed. Imagine that we are trying to build application that's going to different peers, so actually we want to build Oracle, for example. So Oracle in the Web3 world, that's application that tries to go to several price providers, ask for price, then calc average, and return result to particular peer. So it's a classical fork join pattern. You can see it here. Yeah, so we are split our execution on some peer, run these get price in parallel. So I mean, we want to run in parallel, and then join results on some other peer, calculate something, in this case average, and then send this result to receiver. So, and we have language, as I already said, it's called Aqua. And this pattern or this particular application, Aqua, could be represented in literally 6 lines. So here we can go to price services located in different peers in parallel. Yep. Then go to average peer, ask for calculate average, and then go to receiver and send the result to this receiver. If we're talking about the whole stack, in whole stack we have several components. So we have compiler, it's written in Scala. It compiles code written on Aqua to EAR. EAR is our intermediate representation. and TypeScript. And then we have AquaVM. It's our workflow engine. It's written on Rust and compiled to WebAssembly, but it's not necessary. You can run it like in any environment. You can build it on native. It doesn't have any import functions. That's why it's really easy to like embed into some application. But in usual case, it's run inside our execution engine called Marine. That we will talk more on the second part, on the workshop part. And it's interpret this air and like coordinate all workflow across the network. If we're talking about this workflow engine as about like something black box, it could be considered as a finite state machine that takes two states, like some previous state that was obtained for this particular script previous time, and a new state that could came from network. It does some works internally and produce a new state and a list of peers where this state should be sent. So this AquaVM like actually represents the whole business logic that's need to coordinate requests in network, and no one else should should take into account what's going on here. It's should just send this new state to this list of peers, where other AquaVMs, they will take it as a current state and produce some like new state. But what about calling these local functions? For that, we have other bunch of input and outputs. And when AquaVM met like instructions that's intended to call a service locally, it's actually let me show you here. It's actually instruction called call. It's intended to call this local function. When AquaVM met it, it saves all in like needed parameters and then return them as a call requests. And then AquaVM expects that when these compute are ready, they could be run in parallel, whatever. It doesn't matter for AquaVM, for the workflow engine. It's eventually expects them as a call results supplied. Yeah, and the AquaVM doesn't like work in this moment. It's a completely asynchronous process. So it should be run when these call results are ready. And the whole architecture of peer looks like this. So we have libp2p for networking. So we're using Kademli and a bunch of other protocols from libp2p. And our peer from this point of view could be represented as a manager of queues. It also manages resources and do a lot of stuff. But this peer doesn't do any business logic. It's all the business logic compressed in air and handled by AquaVM. So there are two pools of AquaVM for workflow and pools for Marine for services, for local functions. And for example, when AquaVM produces new data with the next peers, then peer core gets from this queue this next peer IDs and send this new data to through libp2p to other peers. Also, like it can produce call requests. Is there any call requests, then peer core like send it to this queue, and this pool eventually handles them and run services. Okay, that's how it works in general. And one of the last slides, it's about AquaVM instructions. Actually, sorry, it's mostly about AIR instructions here because AquaVM is interpreter. So AIR comprises of several instructions. You see that's not a lot. For example, you see here that seek, par, and store, they came directly from PyCalculus. They represent combinators, And actually, it's enough to represent a lot of patterns, and other patterns could be based on these three main combinators. We have much mismatch is also like legacy from PyCalculus. It's for if and else. And we have that something also fold and next. It's the same as a replication. It's for basically for iteration. And also we have more instructions that's doesn't like it's not a legacy or not like came from PyCalculus. It's mostly for working with values. They came from category theory and other like part of abstract math. Okay, and if we're talking about future, so now we support WebAssembly modules, WebAssembly local compute, and we have like workflow engine with our language Aqua to specify workflow and protocols. And we are working on several things. One of the most important that's non-WASM runtimes. It's mainly Docker. Also, we want to bring more languages to WASM. Now there is no GPU support, so we don't, for example, don't prove that GPU allocated in on capacity provider side. We are working on that as well, and we are thinking like about TIA for secret management here, because now all execution is transparent for capacity providers, and for some cases, it's necessary that some secrets should be kept like sorry in secret for capacity providers. And also, like we are working on data integration with different other networks like Fluence, Ceramic, and so on. So it's basically it for part of theory and part of architecture. If you're interested, you can see like some links on the slide, so you can subscribe on Twitter, like ask question on Telegram, yep, Discord. Also, we like launched mainnet in March 20. It's called Cross, and you can find like explore by this link. So we have mainnet and testnet called DAR. That's also like the same template for link. Yeah, that's basically it for theory. Do you have any questions?
Yes, I'd like to also remind that if there will be some questions, just raise your hand and turn on your mic. You can ask your questions with your voice or leave them in the live chat. And if there will be no questions for now, we can go ahead.
Okay, let me share our execution engine. So I wanna ask you, like, do you see it well? Should I like
I see the VS
font
Code.
size? Yeah.
For me, it's readable. For me, it's fine. I'm using a 14-inch laptop, but if somebody has some clues about the font size, just let us know. Write down in the comments if you want the font to be bigger.
I increased it a bit. Okay. By the way, guys, does anyone want to follow me? Like, want to build anything like executable on Fluence? So if someone wants to follow, you need to download this. I will share this repository. So let me send it in the message in the chat. 1 second. This one. So we have a quick starts. I will show you later quick starts, but it will require more work. We don't have like much time. I will show you like basics about our execution engine. And in this repository, you can see some examples of basic functions. But first of all, I need to talk a bit about like WebAssembly and how all of this work. So actually, WebAssembly. So we have concept of service. Service is this local function that's located on a particular peer. Okay, and this function consists of several modules, WebAssembly modules. They are linked together. Let me show you some example. For example, like we have the real simplest service called greeting. This service just greet you, and you see here that's basically that's usual Rust. Sorry. That's usual Rust here, and it's basically the simplest compute for the Fluence network. You just need like several lines, and the most important part here is that you see. I'm not sure like is anyone like familiar with Rust, but I will try to highlight some details. So here we have procedure macro that's wrap this function and tells that this function will be expert, and you can call it from execution engine. And this function, there is a limited number of types that you can use, but actually there are more types that in Wasm Bingen, if anyone like familiar with Wasm Bingen. But strings and all main types are allowed. You can also use your own types. I mean structs. You can define structs and use it as an argument or output type. Sorry. And to compile this one, you need to install Marine. So for that, you need to run carga install Marine. Marine is a CLI binary that's intended to compile modules in an appropriate way. Here you see like simple command, so you can just actually run Marine build, and binary will be built. Also, there is a like fancy directory, so I have it already built. It's a greeting Wasm. It's probably on a different level. Doesn't matter. Let me show you this binary. So we have this binary build. We have in this CLI we have several commands that allows you to work and extract some information from binary. For example, you can see what this binary is about. You can see some information. So here this binary is built without module manifest. It's because it's old one, and you see that I included here. Okay, let me build it. Let me build it with this command. I will show you. Oh, that's for some. Probably it doesn't copy it to this directory. Okay, it doesn't matter, but there will be some information about when this binary built and what is the version of this binary. Also, you can generate aqua bindings. What does it mean? It means that like if you want to like call this Wasm from workflow engine, we need to represent its like signature, all export function signatures, and there is a fancy way to do it. And also you can run it with in a local environment with a REPL. So you can do this one with our Marine REPL. And here there are like a bunch of commands. For example, you can extract imports, or sorry, interface. So there is a, you see it's autocomplete, and you can ask what's our interface. Also, you can call sorry. Okay. I forgot. You can call this module. So to call a module, you need to specify a module name and the function name. So I initially forgot about function name, but they are here. They're the same. You see that it's greeting and greeting. And see the result. That's basically what we are doing here. Concatenate strings. It's real simple service for Fluence. Let me show you more complex example. Example of URL downloader. It consists of several modules. There is a configuration file that allows you to configure your service that could consist of several modules. In previous example, there also was such a file, but there was only one module called greeting. In this example, it's a bit more complex. It consists of 3 modules. Again, it's just an example. It's not a real application. Real applications, for example, SQLite and a bunch of other applications. But for like for terms of like to make it more clear, we'll consider like more examples that not real applications. Here we have like 3 modules. This one that's represent local storage. It's actually just store some files, okay, and could read these files by file name. You see here that this real simple module consists of several functions, and these 2 functions, they are exported. That's wrapped by the marine macro. Okay, and also the second one is a curl adapter. This one, let me briefly explain what is this curl adapter. Yeah, we have several types of modules. There are mainly like modules that we call effector, that require some additional binaries installed, some additional functionality accessible to this module, and pure modules. For example, this greeting module is pure. It doesn't require anything, yeah, from capacity providers. It requires only like WASM to be executed. Yeah, so it's nothing external. This one, curl adapter, it requires, and actually it requires curl. From WASM, it's kind of tricky to use sockets. It's again like it's like work is like only like being done to add this into WASM specification. It's not yet here. It's not yet fully accessible, and there is like this example with using curl, and we can ask like host. Host is a like actually engine that's run this module. We can run an engine. Please give us this import. So give us like a function that will actually be called when we call this import. So from perspective of module, it's import. From perspective of host, it's export. Okay, and we have a special guideline here that's all such host imports should return mounted binary result. They are mostly intended to run local binaries located like on a peer. We are called mounted binaries. So in this particular example, curl binary will be called, and you see here that as part of a config, it's a path to this curl binary. That's because we should point where it's located, which binary should be run actually. So, okay, and there is one export function. So this one is not export, it's wrapped by marine, but it's mostly for tell host that it should be imported. This one is it could be called, it's a download, and actually it's just called curl and provides you a result of this curl. Okay, the local storage is also effectful because you see here it works with a file system. So why actually it's important to differentiate modules? Because for capacity providers, it's important that some modules can be malicious. That's actually this module that works with file systems, that's calls some internal binaries, whatever. But effector modules that don't have imports, they are safe. Yeah, I mean that's why the sandbox works in such a way that you can call only what you're specified in imports, nothing else. And the last module here is called facade. It's a pure module. It provides you just okay, it's a recent. Yeah, I will explain a bit later. It's provide you a fancy way to just like download some. I'm not sure, like some links and store it somewhere on the file system where you specify. Remember that I said that service is actually a bunch of modules. They are linked together. They link with a special like this fancy thing with a module import. So you can specify which which module you want to use in your own module. Here it's both curl adapter and local storage. You specify functions. That you will call. And then you can use it. So it looks like a FFI in Rust, nothing like tricky here, and you can just use it with download and file put. So that's how all this work. And also there are a bunch of other things here. For example, the order of inclusion of modules is important because there could be like circular dependency. We doesn't like deal anyhow with such a circular dependency because it's in this case it's impossible and doesn't need it. And modules should be specified in order of load. So let me show you what we can locally do with curl downloader. I'm sure it's probably built. Yeah, it's a build. So we can load it. We can obtain interface. You see here all exported functions from all modules. So it's curl adapter again, facade, and local storage. So this one called facade, and this actually a module that's accessible, only this module accessible from the Aqua side. Yeah, Aqua can call only this function. So in local, so this mREPL intended for local development. Here we can call any function from any module, but from the Aqua, from workflow engine, we can call only last module here. It's specially called facade. I mean, like it should be facade is a type of module, and here in order, the last module will be one that's exposed export functions to the Aqua side. So in here we can try to call it. Let's say facade, get, and save. Here we have a bunch of arguments. We can specify them in array. For example, let us try to go to download like Google redirection page. Store it somewhere here. Okay, let me. One second. Yeah. We need to call, no, it's here. So this, you see here, that's also there is a sandbox for WASI. It's allowed only to open files inside sites, inside this mapped directory. And the local storage we use this sites directory. Yep, this one that's automatically will be this one. So okay, let me do it again. I guess that's the problem here. That's curl request was because of like my bad internet connection wasn't so fast. Let me try probably GitHub. Something like this. I hope it should work. Okay, no, it not work. It's probably to we should increase this timeout for my for my current internet connection. Okay, it's what I wanna talk about. Also, we have other examples. You can see, for example, SQLite. Here in SQLite, we have. Let me probably. It's not. It doesn't do. So in SQLite here, we're using several modules. It's SQLite, and it's this one that's facade module that uses SQLite with a connector, and there are some examples of like test function that could be called. I see. See, it hasn't been updated. So we have like a bit different. Like we have last release. It's not 14. I'm not sure is it updated. Is it like updated inside the release? But let me. So we have 8 minutes. Yep, if I'm not mistaken. Let me show you more examples. More examples with the workflow engine and with Aqua. I will reshare screen and share you. So if someone interested, you can find more examples here. It's repo code examples. So we have quick starts that's intended to one-to-one like go through application and create both modules. So today we created only modules, only local compute. So then there are like other part to like deploy to the network, to call them, and to write Aqua. So see here that there are some Aqua, simple Aqua examples. Also more marine examples here. You can find more like workflow examples here, integration with different networks, with, for example, IPFS, with DRAND, with NIR. So a lot of here. Yeah. Okay. So probably I should stop here. Do you have any questions? Let me drop this link to the chat.
Okay, so yeah, it seems like we have something like 6 minutes for questions. Please, yeah, if you have any questions, just turn on your mic or raise your hand if there will be a couple of questions, and you can start asking them. And yeah, just a second, let me quickly check out the live chat in other sources where we are conducting our streaming. Okay, yeah, I think there will be some questions after we publish the recording of this session on our YouTube channel. If there will be some questions, I will address them directly to you, Mike. I mean, in written form in the comment section after the recording will be published. And yeah, I'd like to say thank you so much for such an engaging session and for delivering such a great content and making it pretty easy to understand, I would say, even for not for those who are not that deep into the topic. And yeah, thanks everyone who joined our live session right now. I'd like to remind you that we will continue our live sessions back in YouTube. I just sent the link where you can continue watching our stream. And I think that's it for now. Let's see each other in our YouTube link. Thank you, Mike, once again. Hope to see you soon.